Good morning, college algebra. Today we are looking at logarithmic functions. We're going to have a set of notes tomorrow, a final set of notes on Thursday, and then we will meet either tomorrow or Thursday through Zoom to talk about plans for the final. I'm not going to go into a lot of detail about that right now. Just know that we need to meet together to talk about our plans for the final. Which will be either Friday or Saturday. We're going to make a determination on what works best for all of you, but we all have to make sure that the final is taken at the same time by everyone during a single 2-hour window. But like I said, we'll talk about that when we get together for a Zoom class. So you've probably heard me mention before about logarithms, and logarithms they are a fancy way to write an exponent. And you can see that here in the green box. You can take a logarithm. So in this case, we have y equals log base a of x. That's equivalent to x equals a to the y. So just a couple of things that I want you to note. This base of the logarithm becomes the base of the exponent. What the logarithm is equal to becomes the exponent. And whatever value you're taking the logarithm of is what the exponent is equal to. And then that IFF in the middle, that's not a typo, that's a mathematical notation. It simply is shorthand for if and only if. So what that means is that this statement that you see is true in both directions. You can take a logarithm and write it as an exponential, or you can take an exponential and write it as a logarithm. And another thing that's important to note is that the domain of a logarithm is going to be where the property or the character of the logarithm is greater than 0. So whatever you're taking the log of, that has to be greater than 0. And that'll come into play later on here in these notes, and you'll see what I'm talking about. So for example 1, we just want to take each exponential and write it as a logarithm. So I'll try to see if I can't fit everything on the same screen here. So here we have 1.2 to the third power is equal to m. If we write that as a logarithm, we're going to have log base 1.2 of m 3. So we're taking there in the green box, what's on the right, we're going from the right to what's on the left. And that gives us the way to write the logarithm. The one you see here for part B is interesting. Now actually I think I may skip it for right now and come back to it after we do part C. So let's just go ahead and do part C. Part C is log base A of 24 is equal to 4. So like we've said, the base of the logarithm is the same as the base of the exponent. We can just reorganize it however we need to, depending on which direction we're going, either from the log to the exponent or exponent to the log. Now the reason I said part B was interesting is because of the incorporation of e. If we first go ahead and write it out as a logarithm, we get log base e of 9 is equal to b. We traditionally do not see log base e. It actually has its own notation. So rather than log base e, what we would write is natural log of. So anytime you see natural log, it is a logarithm of base e. Something else that I may want to point out too real quick is that if the log base is not expressed, so in this case you see that it's 1.2 and here it's a. If that's not given to you, that base is always assumed to be 10. So if it's a natural log, the base is e. If the base is not expressed, then we assume it to be 10. With example 2, we're going in the opposite direction. We're taking the logarithm and writing it as an exponential. So here for part A, the base is a. The exponent will become 5. And that will be equal to 4. So a to the 5th is equal to 4. For part B, you can see it does say log base e, which like I said a minute ago is not traditional notation. but this would be e to the negative third equal to b. And then for part C, we have the base is 3. The exponent will be c, be equal to 5. So 3 to the c is equal to 5. So using those properties, we can evaluate logarithms without actually having to use a calculator. Now, for parts A and B, both of those can be typed in on a calculator. And I'll show you that here in a second, but let's first go ahead and do it algebraically. So let's just assume then that we can rewrite this as log base 2 of 16 equals y. If we were to write this in exponential form, it would become 2 to the y equals 16. And yesterday we saw how to solve these. The right hand side of this can be written as a base 2 exponent. So what we would have is 2 to the y equals 2 to the 4th. And the only way that this can be true, so we can equate the exponents here, and we just get y is equal to 4. For part B, we're going to do the same thing. We'll set that equal to y, and we can say 3 to the y is equal to 1/27. And the denominator of 27 can be written as 3 to the 3rd. And to pull that out of the denominator, we can rewrite this as 3 to the y equals 3 to the negative 3rd, which is what we were doing yesterday. We were taking the properties of exponents, and here we're applying those properties again to rewrite this in this manner, and then we can just equate exponents, and we get y is equal to negative 3. So that would be the exact value for each one of these logarithmic expressions. Now, I mentioned a second ago we could actually do this on the calculator as well. So if we go to the calculator, open, there we go. And we're doing log base 2 of 16. There's log base A, so now that allows you to type in a new base. So log base 2 of 16, hit enter, and we do find that that is equal to 4. So you can see there, you can use the calculator to do the same thing. I just wanted to show you algebraically how that works as well. And that's going to be kind of a hint maybe for the test or for your final exam. A lot of the things you see on the final can be accomplished with the calculator. So it's important to know how to do both methods algebraically and with the calculator. It's important to me that you understand how the mathematics behind the process works if you choose to use the calculator. And then the second example on that same set, we're going to go to functions, and we're going to go miscellaneous log base A, and here the base was 3. And it was 1/27. See that the answer is negative 3, just as we found algebraically. Back to our notes. Determine the domain of a logarithm. We talked about that just a second ago. Remember I said that the character has to be, or the attribute has to be greater than 0. So what we're talking about there is what we're taking the log of. It doesn't matter what the log base is. What is important is what we're taking the log of. So in this case, this x plus 3 has to be greater than 0. And when we simplify that, we get x is greater than negative 3. So now we have our domain, all x, such that x is greater than negative 3. Or if you want to do interval notation, it is negative 3 to infinity. For part B, going to be the same process. We're going to take 1 plus x over 1 minus x to be greater than 0. Now, what's different about this one is you have to be careful. If we multiply both sides by 1 minus x, we get 1 plus x is greater than 0. We get x is greater than negative 1. The flip side of that too is that if x is, let's say x is 1. Well, if x is 1, this denominator goes to 0 and it's undefined. if x is 2 for that matter. So let's just imagine if we put in a 2. The numerator becomes 3 and the denominator becomes -1. So we get a positive over a negative, and what we see happening here is that the function itself goes to negative. So we can also take and we have to keep in mind that has to be greater than 0, so it can't be negative. So if we take that denominator and also make it greater than 0, what we will find here is that we get -x is greater than -1. We divide through by -1. We get x. We have to flip the inequality, is less than +1. So now we have 2 restrictions on our domain, and we can see that it is bounded between -1 and +1. So we would have our domain would be in interval notation, -1, +1, or in set notation, it's all x such that x is between -1 and +1. And then for part C, absolute value is always going to be greater than 0 unless x itself happens to be 0. So 0 is the only value that we cannot include. So we can have -infinity to 0, then 0 to +infinity, because any other value for x, what we're taking the log of in this case, will always be positive. And then again in interval notation, or set notation rather, we have x such that x is less than 0, x is greater than 0. Graphs of logarithms, this is going to be just a lot of calculator work. So we'll just jump right down here to example 5. It says first find the domain of the function f of x equals negative natural log of x minus 2. So for part A, we just take the x minus 2. It has to be greater than 0, and that implies that x is greater than +2. So there is our domain. The graph of f, we would just use the calculator. It's negative natural log of x minus 2. Clear these out. Natural log 2. And there's your graph. You can see that it has a x-intercept of +3, has a vertical asymptote at 2, which is what we would have expected given that the domain is greater than 2. And so we can graph this on our notes. Vertical asymptote here at 2, have an x-intercept at 3. So our graph is going to look something like this. From the graph, determine the range and vertical asymptote of f. Well, we know the vertical asymptote is x equals 2, and the range is going to be all real numbers. This graph is defined all the way up to +infinity and all the way down to -infinity along the y-axis. Part D asks you to find the inverse of that function. And so to find the inverse of any function, we first write out the original function as y equals negative natural log of x minus 2. To find its inverse, we simply replace x with y and y with x. So now we rewrite it as x equals negative natural log of y minus 2. And here we would solve for y again. So the first step would be to divide both sides by -1. So that gives us negative x equals natural log of y minus 2. And then the only way to get rid of that natural log is to basically exponentiate both sides of the equation. And we would write this now as e to the negative x equals y minus 2. That's how you get rid of the natural log. And then we would add 2 to both sides, so we get e to the negative x plus 2 equals y. And there's our inverse of the function. Use the function, the inverse, to confirm the range found in part C from the domain. All this is simply done by part F, where we just graph this. So we would graph e to the negative x plus 2, and I'll graph that on the same axis as what we have here. So it's going to be e, that's going to be negative x plus 2. And there is our function. And we can see they do intersect, but these graphs are mirror images of one another across the line y equals x. That's how we know they are inverses. There's your graph, the black line, y equals x. And so because they're mirror images over the line y equals x, we can see that the natural log and the exponential are inverses of one another graphically. All right, keep on moving. And so example 6 is going to be similar to example 5. First, we want to find the domain. So again, to find the domain, we just take x minus 1 is greater than 0. So that gives us x is greater than 1. So our domain is all x, such that x is greater than 1. We want to graph the function. Not going to go through that again. We know how to use the calculator now. So if you want to verify that, graph this on your calculator. 3 times log of x minus 1. And then we want to determine the range, vertical asymptote. Well, we know the vertical asymptote is going to be at positive 1. And we want to find the inverse. That's what I really want to get to. So once again, we have y equals 3 times log of x minus 1. And we rewrite it as x equals 3 times log of y minus 1. And we solve this for y. So again, the first step, we're going to divide both sides by 3. And just like when we talked about the rewriting logarithms as exponentials and exponentials as log, like we did in example 5, here the base of the logarithm is 10. So we know that this is going to be 10 x to the, or x over 3 equals y minus 1. And now we can add 1 to both sides. We're going to get 10 x over 3 plus 1 equals y. And there's our inverse function. So solving logarithmic equations means that we have to understand how to rewrite logarithms as exponents and vice versa. So here we're going to do for example 7 part A, we take the base of the logarithm, raise it to the second power, and set that equal to 4x minus 7. 3 squared is 9. Now we can add 7 to both sides, divide by 4, and we get x equals 4 for part A. For part B, we get x squared equals 64. Take the square root of both sides, and we get x is equal to plus or minus 8. Now, we know that that is true. Plus or minus 8 solves this equation. However, it does not solve our original logarithm because we cannot have a negative base as our log, or for a logarithm. So here we just simply go with x is equal to positive 8. Example 8, we're using e as our base. So it's just like what we've done in the past. There is also a helpful note over here, e to the y equals x, then y equals the natural log of x. So what we would have is 2 times x equals the natural log of 5. Divide both sides by 2. and we get x equals natural log of 5 over 2. Now this is an exact answer, and typically that's what you want to give, is the exact answer. If you were asked to approximate it, you could just type that in on your calculator. Natural log of 5 over 2. Clear these out. Natural log of 5 over 2. That wrong. There we go. Natural log of 5 over 2 is 0.8047. So that's the approximate answer. Okay, so just keep in mind there is a difference between exact and approximate. The natural log of 5 over 2 is our exact. The decimal approximation obviously is the approximate answer. And then finally we get to example 9, and this is the last example for today. We're talking about blood alcohol concentration. We're given a formula that illustrates the relative risk of having an accident while driving a car, dependent upon blood alcohol concentration, where X is the percent of the concentration of alcohol in the bloodstream and K is some constant. So for part A, and these should be labeled, I don't know why I have bullet points here, B, C, and D. For part A, it says research indicates that the relative risk of a person having an accident with a blood alcohol content of 0.02 is 1.4. Find the constant K in the equation. So we take part A here. We take our equation, E, K times X. We're going to replace R with 1.4, that's the risk, equals E to the K times 0.02. We're trying to solve this for K. So we're going to take the natural log of both sides to get rid of the base of E. We have natural log of 1.4 equals K times 0.02. We would divide both sides by 0.02. So I'm going to use the calculator for that. The log of 1. Divided by 0.02, and we get 16.82. So there's our constant K, is 16.82. And we're going to use that value throughout the remainder of this problem. So for part B, it says using this value of K, what's the relative risk if the concentration is 0.17? So here we're solving for R. We have E is 16.82. That's our value for K that we just computed. And our relative risk is 0.17, or our blood alcohol concentration is 0.17. So when we simplify this using the calculator, we have E to the 16.82 times 0.17. times, do it in parentheses, 16.82 times 0.17, and we get 17.45. So that's the relative risk. So there's a 17.45% chance of having an accident with a blood alcohol content of 0.17. Where are we at now? Part C. Using the same value of K, what BAC, or blood alcohol content level, corresponds to a relative risk of 100%. So for part C, we have 100 equals E to 16.82, and we don't know what our value for X is. So we're going to take the natural log of both sides, get rid of that E, and then we would divide the natural log of 100 by 16.82. And so we have to go back to the calculator. natural log of 100 divided by 16.82, and we see that a blood alcohol content of 0.27 is going to be 100% relative risk of having an accident. So what was it again? I forgot already. 0.27. So blood alcohol content of 0.27% will correspond to a relative risk of 100%. And then finally, for part D, if the law asserts that anyone with a relative risk of 4 or more should not have driving privileges, at what concentration of alcohol in the bloodstream should a driver be arrested and charged with a DUI? So part D is very similar to part C. A relative risk we know to be 4, and we want to look at e to the 16.82. Again, we don't know what x is, so this is going to be the natural log of 4 is equal to 16.82x. That means x has to be equal to the natural log of 4 over 16.82. And we go back to our calculator. I'm just going to reuse our equation here and be lazy. Place that with 4, we get 0.08. So a blood alcohol content of 0.08 would be the point at which someone should be arrested and charged with driving under the influence. That is the end of the introduction to logarithms. We're going to be working more with logarithms over the next 2 days, leading up to the final. And there's your suggested problems, so take a look at those. If you have questions, ask me. Otherwise, I'll be talking to you guys tomorrow, and I hope everybody's doing well.